Hello students, today we will learn how to calculate the electric field at a point P as shown here in the sketch. P is R meters above the center of a uniformly charged rod. We know that the rod carries linear charge density and we will name it lambda. The rod is of length 2L. So we placed it in a way that the first end of it lays at negative L and the second end lays at positive L. So there is some symmetry here. If this is the origin O, the distance between O and L is equal to the distance between O, the origin, and minus L. When we are interested in the electric field at point P. As usual, when we deal with continuous charge distribution, we usually take a small piece of the rod that carries a charge dq, let me name it dq1, and the length is dl usually, but because here the rod lays on the x-axis, I can name it dx. And to get use of the symmetry, I will take also another piece here, dq2. So this is also of length dx. The distance between the origin and the piece that I chose is x, and here also is x. So I took two pieces that are at equal distances from the center or from the origin, equal distance. So I will start checking the field caused by dq1. I'll imagine an imaginary tested charge here. So this is dE1. This is the small field generated by dQ1. And also here I will have dE2, because a positive test charge at P will be repelled from dQ2. For sure, if the rod is negatively charged, these arrows will point down. Now we will check the resolving of these two vectors. dE1 will have a horizontal component or an x component and a vertical component, dE1y. Similarly, for dE2, it can be resolved to a component here, dE2x, and here dE2y. As you can see, these two components on the x are equal and opposite, so they cancel out. So as if I am telling you that the field at point P is only due to y components. So let us keep this as a note. X components will cancel out, and I need to study only the small components generated from the vertical components. So dEy will be equal to k dq over the distance, this distance, let me name it small r, distance between the point and the charge, so r squared, sine theta. Sine this angle, which is also this angle here. So sine theta, as we are used to say that the y component take the sine of the angle with the positive x-axis. So if I want the total E, I will integrate. So total electric field will be the integration of the small pieces of the electric field. Integration is like summation, so it will give me the total field. R squared sine theta. Now here I have a problem actually, that I have Q and theta and R. I have a lot of variables. So I need to somehow reduce or write the variables in terms of each other. So I will start with the vector R, which is just the hypotenuse of the triangle here. The hypotenuse of this triangle. So it is radical x squared plus r squared. X is this side and r is the distance here. So x squared plus r squared. Also sine theta, to reduce the, I don't want the theta as a variable here. So sine theta is opposite over adjacent, so it's r over capital R over small r. Also, we can use for small r radical x squared plus r squared. So my goal here is to not to have a lot of variables. dq using the linear charge density is lambda dl. We know that lambda is defined as dq or q over dl with some cross multiplication. So lambda dx. We named that the size of each small piece is just dx. Let me try to plug these here and see is the problem simpler or no. So I will have here equal, e will equal to integration lambda dx divided by r squared. So radical squared, the radical will be removed, x squared plus r squared. Instead of sine theta, I have r over radical x squared plus r squared. Now here actually the problem is much simpler because I have dx means I am integrating the x variables, and the only variable I have here is just the x. R is a constant. The height of the point above the rod is just constant. So let me do some simplification. I will take out the constants. Also here I have r. I'm left with the integral of dx divided by, notice that this one can be rewritten as x squared plus r squared to the power of half, and this one is to the power of 1. So if I will add both powers, I will get x squared plus r squared to the power of 3 over 2. So 1 plus half is just 3 over 2. So here, as if I am multiplying the same base and adding the powers. Here, let me check the integral limits. For sure, the first piece that I can get is here at the point minus L. The last piece at positive L. So from minus L to positive L. Here I need some calculus. I need some help and to go and figure out how to integrate this integral. Usually, as a rule, if you are integrating 1 over a, where a is any constant, squared, plus x squared dx, so 1 over reciprocal of two terms that are squared, this will give me x divided by a squared times a squared plus x squared to the power of half. I will not ask you to memorize this. I will be giving it to you if we need it. So I will be substituting here the answer. So I have k lambda r. Then the answer of the integral is x divided by the constant a here is r. I have only this constant, which is r. So I have here x over r squared, x squared plus r squared to the power of half, which is just radical. We can keep it power of half because it's simpler when we plug in the limits of the integral. Now, as usual, you will start with the upper limit substituted instead of x minus the lower limit substituted instead of x. So I will keep these math steps as a practice for you and will give you directly the final result that I advise all of you to memorize. The final result will be 2k, notice that here this r will be crossed with the square, 2k lambda multiplied by L, where L is half the length of the rod because the length of the rod here is 2L, divided by r, the distance above the rod, radical r squared plus L squared. So this is the final result. Notice that L is half the length of the rod. Now, sometimes in the problem, it's better to substitute k as 1 over 4 pi epsilon 0 and do the simplification. And in some problems also, they give you q instead of lambda, so you substitute q over the length, which is here 2L, instead of lambda. So just keep these points in mind, that here I named the full length of the rod as 2L, and L in the formula is half the length of the rod.